So a voltmeter reads 80 volts when connected across the terminals of a sinusoidal power source with frequency 1000 hertz. Write the equation for the instantaneous voltage provided by the source. So it simply means that a voltmeter is connected across an AC source. Once the source is a sinusoidal, okay, once it's a sinusoidal power source, then it's an AC source. The frequency of the source is 1000 hertz. And last time, I explained to you that the difference between AC and DC is how one has to do with how both of them are produced. Inshra, how do we obtain direct current? How do we generate DC? Nanama Inshra.
Please, DC is produced from the chemical reaction between an electrode and an electrolyte.
So whenever there's a chemical reaction between or a reaction between chemicals or electrolytes being in a liquid form or in a paste form, and an electrode, carbon, zinc, magnesium, copper, these are electrodes. Okay, then direct current can be produced. Now, how do we produce AC? For how do we produce AC?
See that, please, I don't know.
Babo, you don't know, say. Don't you watch the videos?
Yes, please, but I don't recall having that one.
Ah, where I do the AC diagram, AC generator. Okay, Nanama, Inshra, how is AC produced?
You should say that AC is produced when a coil, which is supposed to be a conductor, rotates at a constant angular velocity within a uniform magnetic field.
That's it. So now therefore I'll go back to read the AC theory videos. Okay. So
Yes,
when a
please.
coil rotates at a uniform or constant angular velocity within a uniform magnetic field, alternating current is produced. So how the coil rotates is its frequency. Frequency is number of cycles per second. So the frequency given is the rate at which the coil rotates, okay, in a uniform magnetic field. So we are told that this coil rotates, okay, 1000 times within 1 second. That's the meaning of 1000 hertz. 1000 times number of rotation within 1 second. Okay, so we have to write the equation for the instantaneous voltage provided by the source. Very simple question. You see, we've gone through AC alternating current is harmonic function. So if you recall, when we're doing simple harmonic motion, I said that one of the examples of motions that are simple harmonic is a movement of electrons in a conductor. Nana Jemfua, do you remember that I said an example like that?
Yes, please.
Good. So this is the movement of electrons in a conductor is what forms alternating current. So AC is also harmonic, meaning it's a sinusoidal. It's represented by a sine function. So if you are drawing something to represent alternating current, this is it. Okay. This is the peak or the peak current. What in the displacement equation of the body executing SHM, we said this is the amplitude. But in terms of current, you said this is the peak current or the maximum current. So if it's a simple harmonic motion, its displacement is given by this A sine omega t. When it is starting from the origin, okay? Because alternating current is also a harmonic function, alternating current is represented as this. I is equal to Im sine omega t. Almost the same as displacement equation. And they are similar because they are all harmonic functions. Please, do you understand? I hope you are following.
Yes, sir.
Yes, please.
Okay. So this is what we call this I subscript small I, or what? This is known as instantaneous current. In SHM, how would you find Y? If you have this, how would you find Y? Gerard, can you help? In simple harmonic motion, how would you find this Y?
So to find the y, you compare it to the I is equals to Im sine omega t.
No, I'm just in SHM. How would you calculate for the displacement Y? I'm not connecting it to the current, but in a simple harmonic motion, how would you find Y? How would you find the displacement Y? Now, you have any idea as to how to find the displacement Y?
You input the sine omega t.
So when you know the time, amplitude is always fixed. Omega is always fixed. So when you know the time, you can always substitute it into this equation to find it. So in terms of displacement, we will say that Y is the displacement in any time t, or the instantaneous displacement. Please, do you follow? Okay, because we can always find Y when the time is known. We can also say that Y is the instantaneous displacement. Sort of bring I here. Because of this, we refer to this I as instantaneous current, meaning current within a given time. Current within a given time. So we say this I is the instantaneous current, whereas I subscript M, we say this is the maximum or peak current, or peak current. This is also the same as in displacement. We say A is the amplitude. The amplitude is the maximum displacement. So this is the measure from the equilibrium position to this point is what we are referring to as the maximum or the peak current, or what is here. Please, are you okay? Are you okay?
Yes, please.
All right. Omega is the angular velocity. When a coil rotates at a constant angular velocity within a uniform magnetic field. This instantaneous current equation can also be written as this. I M or P or not sine, because omega is equal to 2 pi f, we can also write it as sine 2 pi f t, or I am sine 2 pi over t times this as the instantaneous current. Now, whenever current flows, there must be a voltage. The voltage is the pressure. Current is similar to flow of water. The voltage is similar to the pressure which pushes the water. The resistance is similar to the diameter of the pipeline or of the tube within which the water flows. When the tube diameter is larger, resistance is small. When the tube diameter is smaller, resistance is high. Okay, so for current to flow, there must be a source of voltage or EMF. That is why Ohms said that voltage is directly proportional to current flow. So if you have instantaneous currents like this, then there must be instantaneous voltage, which pushes the charges to create the current. Class, are you okay?
Yes, sir.
Yes, please.
So whenever there is current, there must be a voltage. The reason for which one of the conditions for current to flow is that there must be a source of EMF. The EMF is the voltage of the source. So if there is instantaneous current, there must be instantaneous voltage. So we equally have V and its nature. Its nature is also harmonic. So we represent voltage in a alternating voltage, or yes, alternating voltage as sinusoidal, harmonic, a sine function, just as we represented current. Once it's a sine curve, start from the origin, where this is the peak voltage or maximum voltage, either from here or from this part, minus. So it has the same relationship as current. And because this is a harmonic function, it is represented as the displacement equation of a simple harmonic motion. So V is equal to Vm sine omega t, where V is this is usually represented as small v, instantaneous voltage. Instantaneous voltage. And then Vm is the maximum voltage or the peak voltage. Peak or maximum voltage. And so the instantaneous voltage equation the instantaneous voltage equation can equally be represented or written as V is equal to Vm or Vp or not sine 2 pi ft if you substitute omega, or V is equal to Vp sine 2 pi over t times this. So let's go back to the question. A voltmeter reads 80 volts when connected across the terminals of a sinusoidal power source with frequency 1000 hertz. Write the equation for the instantaneous voltage provided by the source. Start work.
Mr. Dad, please, I want to see the diagram.
Okay. So after talking for that long,
Mr. Adrian,
hello,
please the question.
I sent it to the group. Oh, it's on the platform.
Okay.
Okay. Okay. Did it?
Mr. Adrian,
Do you have the question?
no, please.
I've sent it to you.
Thank you.
Priscilla, have you received it? Or have you seen the question?
Yes, please.
Two minutes. 2 minutes more.
Mr. Adrian, what I saw is not that one. Please, can you resend it?
The what?
The question, what I said I've seen is not that one.
But aren't you on the group?
I'm there, but I've not seen it.
Ah, I've just sent it twice to you. Priscilla,
Okay, let me.
or you are not the one. Okay, I'm sure you finished. Eh?
Yes.
Ishra, Nana Jemfua, Edith. Are you true? Hey, everybody is quiet too. So, Gerard, give me your answer.
So please, I had V is equals to 8 sine 2 pi c
2 pi,
2000 pi, sorry,
2000 pi
c.
t. Okay, Inshira.
Yes, I got the same thing.
Nana Jemfua. Nana Jemfua. Where is Nana Jemfua?
Please, I'm here. He's also got the
What?
same thing.
Okay. Let's see. Let's see who is right. Now, the instrument measures the effective current and voltage. So if I use an ammeter, if I use a voltmeter, what I measure is the effective voltage or current. So the instrument, and I told you that the effective current and voltage is also known as the what? Yes. What name do we give to the effective current or voltage? Okay, here, let's connect it to voltage. What name do we give to the effective current or voltage reading? Eh? Yo. I said the effective voltage is the RMS value, VRMS. The root mean square voltage. That is the effective voltage or current. And this is what the instrument reads. This is also known as the main voltage or effective voltage. So when you use a voltmeter to read voltage drop or EMF, you are measuring the effective voltage. You are also measuring the RMS value. Two, if you measure voltage or current from the source, if there's a socket, there is a socket. You are the socket is the mains. Okay. When you measure voltage or current from the source, it is also the root mean square voltage or current. Okay. So we refer to them as the effective voltage or the main voltage, effective current, or the main current. Please, are you okay?
Yes.
So
Yes,
note that the instrument, whether voltmeter or ammeter, measures the effective voltage or current, which is also the root mean square voltage or current, or the current or voltage from the mains. All right. So if what the instrument is measuring is the root mean square voltage, you know, for instantaneous voltage V, it must be equal to Vm, the peak or maximum current, times the sine of 2 pi f times t. So you need to know the peak voltage or the maximum voltage, then the frequency. As for t, it is instantaneous, so within any time t. So once I have the reading from the instrument, which is the RMS value, VRMS, which is 80 volts, I use the relationship between RMS value and peak value. And Inshira, what is the relationship between root mean square voltage and then the peak voltage? What's the
What did
relationship?
you say?
What's the relationship between root mean square voltage and then the peak voltage or the maximum voltage?
Um, it is the root mean square voltage is equal to maximum voltage over root 2.
Thank you. So this is, we have Vm over root 2 or Inshira,
Or 0.7071 Vm times the maximum voltage.
So we have this and we are looking for this. Look at it again. 2 minutes, start work. And let's see if you get a different equation. 2 minutes.
I'm getting V naught is equals to H root 2 sine omega t.
Come again.
H
No,
root 2
give me a whole number. I don't need a fraction. Give me a whole number.
Okay, so whole number, that's 11 whole number, 11 sine omega t.
11.
Yes, sir.
Do it well. Open your eyes. Now, therefore, what have you had?
Please, I'm still on it.
Priscilla, what have you had? Irene. Edith.
Could you repeat that? V naught to be equal to 113.
Is it one? Okay. So then write the instantaneous equation for me. So Gerard, it is 113. The maximum value is 113. Sorry, root 2 times 80, right? Root 2 times 8. Let me confirm myself.
Is it 80 or 8? Because in the question is 80.
It's check, right? I said 80. 80. Hey. Oh,
Maybe I had the same answer.
as what?
So 113
Yeah,
sine
so
omega
please, when you are doing this thing, yeah, please be careful. Open your eyes to get the right thing done. So V peak or maximum is equal to 113 volts. Therefore, the instantaneous voltage V is equal to 113 sine of frequency is 1000. So 2000 per T. Or you can choose to multiply 2000 by pi and then express it in. So this will be the instantaneous voltage. Irene understood.
Yes, please.
Hey, understood. Edubia.
Yes,
Did it?
please.
Yes, please.
Okay. A second question. Please, if you have any question, quickly ask and let's continue before I post you another question. Any question? Okay. Once everybody is silent, it means you have no question. I'm going to send you another one, and I don't expect you to falter in this. You must get it right. Current and voltage are expressed in RMS values. That is the effective value. So take note. Okay, so I've sent another question. I'll send it to you. I've sent another question. Please check and confirm if you have received it. So a voltage V is equal to 60 sine 120 per T is applied across a 20 ohm resistor. What will an AC ammeter in series with the resistor read? A voltage V is equal to 60 sine 120 per T is applied across a 20 ohm resistor. What will an AC ammeter in series with the resistor read? Just make me proud. In how many minutes? Make me proud within how many minutes?
Please, I don't know.
I want you to give me minutes or give us minutes to try. Okay, Nana Jemfua, how many minutes? Within how many minutes time?
7.
Hi, 7 is too much. Okay, 5. Start with. Okay, so we shall see. Gerard, we shall see whether your answer is correct or not. So, Inshira, what did you get? What's the final answer?
I think it's my final answer.
Hey, Nana Jemfua. Nana Jemfua. Idiot.
Yeah,
Idiot. What?
please, I had 2.12.
Okay, we shall see. Then Priscilla, you had, so you had what? 3. Who else? Let me see. Irene. Irene. Yemfua, you can't hear me. Okay, so let's see. Let's see if the answers you have given me is correct. So a voltage V is equal to 60 sine 120 pi t. So the instantaneous voltage is 60 sine of 120 pi t. It's applied across a 20 ohm resistor. So R is equal to 20 ohm. What will an AC ammeter in series with the resistor read? So what we are looking for, the current. What will an AC ammeter? An ammeter reads current flow. Okay. But here, since it is the reading of the instrument, I said the instrument reads root mean square value of the current, which is the effective, okay, value of the current. So what the instrument reads must be the RMS value. Okay. Now looking at RMS value is equal to VRMS over resistance. The current, the voltage must be in terms of RMS value. So from Ohm's law, V is equal to IR. So VRMS must be equal to IRMS times resistance. Therefore, if you are looking for the ZZ, now from the equation, I can find the peak or the maximum value of the voltage, which is 60 volts. Knowing that VRMS equals V maximum divided by root 2, I have 60 over root 2. And this is times root 2 over root of 2. So I have 60 root 2 over 2, which is the same as 30 root of 2. Okay, so IRMS therefore is equal to 30 root 2 over resistance, which is 20. So I have 3 on 2 root of 2, and this is equal to 2.12 ampere. So Gerard got it right, Edith got it right. And now mention
Mr. Idea.
this is what you need to have. Okay.
Yes, please.
Now, what is wrong with the Infua's connection? Okay, were you able to do it? Okay, so let's continue. So we have done a bit of trials, applying what you've learned in solving problems. Let's continue with our conceptual build-up. So in our last meeting, we look at the effect of AC on circuit components such as resistor, inductor, and then a capacitor. We'll review it quickly and move on. So when you connect a resistor to an AC source, so the source is here. I told you in a circuit, if the source of EMF is AC, this is how we represent it. Connected to a resistor. And this is a purely resistive circuit. A purely resistive circuit. So in a purely resistive circuit, we have only a resistor connected to a source of EMF. Current, an AC source has no positive terminal and has no negative terminal because the directional flow of the current changes with time. So when we connect a voltmeter across this to find the voltage drop across the resistor, this obeys Ohm's law. So we realize that V across the resistor is always directly proportional to the current flow. Okay, and because of this relationship, we say that the current I, or for a purely resistive circuit, for a purely resistive circuit, current is in phase with the voltage drop across the resistor, or potential difference across the resistor. And when two quantities are said to be in phase, what it means is that they occur at the same angle in the same direction. Okay, those two quantities rise and fall together. They all rise, okay, from 0 to their maximum value together. So if there's the starting point, they all rise, increase steadily, get to a maximum height or level, and then fall to 0. So it's about two quantities. So the other quantity would also start from the same point, rise steadily, gets to the maximum value, and then drop to 0, just as the second quantity is. So this is the first quantity, this is the second quantity. So they rise and fall together, meaning, and that indicates that the two quantities are in phase. So the phasor diagram of voltage across the resistor and then current in phase. This is what we had, that the direction of current is the same as the direction of voltage. And phasor diagram, we are representing the direction and then the magnitude on the in the Cartesian plane. So current direction I is the same as the voltage direction VR. This is the phasor diagram. So for purely resistive circuits, we usually represent it as just these two lines. Here's the phasor diagram. Now the waveform, apart from their phasor diagram, they also have another representation, which is the waveform. Let's draw it for the waveform for the two quantities in phase. Their waveform. Alternating current is represented as I maximum or peak omega t. Alternating voltage V is given as Vm sine omega t. And here we are connecting a resistor across the circuit, but because this is the only component within the circuit, the voltage drop across the resistor is certainly equal to the source voltage. Please, are you with me? Hello?
Yes, please.
So we have the voltage drop across the resistor equal to the source voltage V, because this is the only component within the circuit. Okay, so the instantaneous voltage representation is simply the same as the voltage drop across the resistor. So this is the harmonic function for the current. This is the harmonic function for the voltage drop across the resistor. Now, when you draw on the graph, this is a sine function. They start from 0. So now so this is for I, current. Now the voltage drop across the resistor is also the same thing. Okay, it's also a sine function, and we'll start from the origin. Let me draw this properly. So this is also a sine function starting from the same point. So it will also begin at this same point, get to the maximum, fall to 0, start, get to the maximum, fall to 0, just as the current is also behaving. Okay, they say one just lies on the other, but I can't draw it. I can't draw the second one on the first, or else you won't see any difference. The reason for which I'm representing this in a broken line fashion, just to create the distinction. So this is VR. So this is the waveform for the current and then the voltage drop across the resistor. Okay, it starts at the same point and then fall together. And this is the phasor diagram. I as against VR. Please, any question? Are you okay?
Yes,
Class, are
please.
you okay? All right. So if we are for a purely resistive circuit, the source voltage is the RMS value. Don't forget. And the current through the resistor is also the RMS value. So we extract that, then the resistance of the resistor is equal to VRMS over IRMS. And we are all familiar to resistance. SI units ohm. But to find that, we must always express this in RMS value. Please, it's because we are dealing with alternating current. If it is DC, we won't talk about root mean square values.
Mr. Yeah.
Hello.
So you said when voltmeter and ammeter, they always measure in for AC, they always measure in RMS value.
They always measure the RMS value. They measure the RMS value, which is the effective current or voltage.
Oh, okay.
So whenever you are to calculate for maybe the ammeter reading or the voltmeter reading, don't forget it is the RMS value that is being required. So if other quantities are given to you, maybe the peak value, instantaneous value, you need to express it in RMS value. That's what I mean. All right. Then let's look at alternating current through an inductor. Or, okay, let's rather talk about the AC through a capacitor first. So a purely capacitive circuit. So in a circuit, a capacitor is represented as vertical lines, equal vertical lines. Or this. This is the old capacitor representation. But the common ones in most circuit diagrams is this. So for a purely capacitive circuit, we have a capacitor connected to AC. So this is the source voltage V. Sometimes there is indication of the frequency. Then this is the capacitor. And a capacitor, we know a capacitor to be a device that stores charges. So a capacitor is an electronic device that stores charges. It is made up of two parallel plates. So this thing you see are two plates, parallel plates, with something a non-conducting material in the middle, known as a dielectric. So a capacitor is made up of a capacitor is made up of two parallel plates and a non-conducting material sandwiched between the two plates, known as the dielectric, so what is in the middle is a dielectric. Because the dielectric is a non-conducting material, this is the reason for which the conductor can store charges. Because if it conducts, okay, it easily conducts, then the charges can, when put on one plate, can just pass through another plate and then go. But what is always in the middle doesn't allow charges to move unless there's a higher potential gradient between them. So this is the composition of a capacitor. Before we look at, let's look at some of the uses of a capacitor. What are some of the uses of a capacitor? Everybody should give me one usage of the capacitor. Let me start from Gerard. Gerard, give me one of the applications or usage of the capacitor. Hello. Hey, can you hear me? Edit. Edit.
Mr. Asia,
Talk. Give me one usage of a capacitor. Where can we see the application of a capacitor? Edit, are you there? Hey, everybody is quiet here. Isra,
Yes, yes, Mr. Apia.
one usage of a
Of
capacitor.
We said that the capacitor is used to store charges.
So, you see, all devices that stores charges for a while has a capacitor within as part of its circuitry. So most electronic equipment have capacitors. These days are your LED, LCD TVs. When light goes off, it's able to withhold or stay on for some time and then go. Our laptops, okay, mobile phones, iPads, UPS, uninterruptible power supply, UPS. So all devices that stores current or that works on DC, especially those devices that are rechargeable, okay, all you make use of capacitors. You all make use of capacitors. Then two, apart from this storage of current for a while before it goes off, capacitors are also used in ceiling fans. The ceiling fans in our rooms have capacitors within. Okay. And finally, capacitors are also used in power factor correction. Power factor correction. And here you won't understand so much unless when we get to that concept, I explain. It's also an ACT, or when we get there, I'll explain. But capacitors are also used in power factor correction, correcting power factors. It is used in ceiling fans, okay? It is used in this devices that stores power or current for a while before it goes off. So in UPS, uninterruptible power supply, in laptops, handtops, all devices that are rechargeable, okay, have capacitors in there which stores the charge, so that when power is off and you want to use your laptop, you use the energy stored, which is the laptop battery, and that will be supplied till the charger stored dry goes off. Please, are you okay?
Mr. Elia,
Yes,
please,
sir.
what was the third use of the capacitors?
What is that?
The one you
The
said
what?
the one you said we don't understand. I didn't write that one.
I said that in power factor correction. Power factor correction. Because you haven't done it. That's why I said power factor correction. In power factor correction. Gerard, are you there?
Yes, sir. Yes, sir. So I had to do
So-
some small things.
Are you okay with all that I've said?
Yes, sir.
Nana Jemfa, talk to me. Irene, Priscilla. All right. So a purely capacitive circuit. So in a purely capacitive circuit, what we are doing is that we are passing alternating current through a capacitor to see its influence. What happens when we do that? I remember last time I connected this to passing direct current through a DC.
Mr. Elia, please, can you go to the other side of the board?
Is it okay?
Yes, please.
So I explained the purely capacitive circuits using a capacitor connected to a DC source. When you connect a DC source, a battery, to a capacitor, what happens is that when you connect a DC to a capacitor, this is the EMF of the battery. We have here as the voltage drop across the capacitor, VC. When you do this, what happens is that the charges builds up on the plates. So minus, 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 minus. Okay, so the charges are stored on the plates. But because of the dielectric, the positive, the negatives do not establish contact. Okay, it builds up on the plate, all right, but because of the dielectric within, they don't establish contact to neutralize. Now, you realize that as the charges get built up on the plates, the voltage drop across the capacitor, delta V, with time, you realize that, okay, the voltage drop across the capacitor will be directly proportional to the external voltage or the source voltage. At a point where the two are equal, then the capacitor is said to be fully charged. Capacitor is fully charged. So a capacitor gets charged when the voltage drop across it is equal to the source voltage. Now, as the charges builds up, you realize that Q, which is the charge on the plate, is directly proportional to the potential difference is equal to directly proportional to the change in potential difference across the capacitor. So as Q increases, the voltage drop across the capacitor also increases. Okay, then when delta C is equal to the source, then we say that capacitor is fully charged. Then it is disconnected, work is done. Once it's fully charged, work is done. So Q, if Q is directly proportional to VC across the capacitor, then Q is equal to K times delta V. K therefore is equal to Q on delta V. K is what we call as the capacitance of the capacitor. So C is equal to K, which is known as capacitance of the capacitor. And the capacitance of the capacitor is the measure of the capacitor's ability to store charges. That's the definition. The measure of the capacitor's ability to store charges is what we call as the capacitance of the capacitor. The measure of the ability of the capacitor to store charges is known as the capacitance of the capacitor, which is given by charge over the voltage or voltage drop or the potential difference. The SI unit of the capacitance of the capacitor is the farad. Farad, shortened as capital F. All right. So when you connect a DC, to a capacitor, the capacitor gets charged. Now, when you connect an AC, what happens? Let's see what happens. When you connect an alternating voltage, what happens is that over here, the alternating current, okay, will lead the voltage drop across the capacitor, VC. So in a purely capacitive circuit, voltage drop across the capacitor which is VC, lags behind the alternating current. Alternating current, or the other way around. The other way around is that the current leads the voltage drop. So when the current goes up, start from 0, goes up to a maximum, okay, capacitor, the voltage drop across the capacitor isn't there yet. So when the current reaches its peak through one cycle, the voltage drop across the capacitor so small that when it starts at the other cycle, it is like positive canceling out negative. No work will be done. So in one cycle flow of the current, voltage drop will be building up gradually. If it has obtained maybe small delta V, in another cycle flow of the current, the opposite cycle, because the directions are opposite, we have the same voltage drop buildup, but in the negative. This is positive, whereas the other one is negative, and the two cancels out. So in effect, over one cycle, no work is done. So if you charge a capacitor with an alternating current, no work is done because the capacitor gets charged during one cycle and also gets discharged during the other cycle. So if you connect a voltmeter across it, you see that the potential difference across the capacitor is 0. Please, are you okay?
Yes, sir.
So the capacitor gets charged in one cycle and also gets discharged in the other cycle. Okay. That is why if you use DC, because one directional flow, it will just charge during that flow. And there's no other cycle flow to discharge it. So it will be stored. But this one, in one cycle, charge is stored. In another cycle, it is cancelled. And so it will no work will be done. So applying AC to a capacitor, this is what happens. Here, in charging a capacitor, alternating current becomes a nuisance to it because it doesn't work. Okay, so this is some of the applications where alternating current is not needed. So charging a capacitor does not need AC, it needs DC. Another application which always needs DC is separation of ions, electrolysis. Electrolysis also does not need AC. It always will require a direct current. Please, if you have any question, ask. Let's go into the mathematics of purely capacitive circuits. It. Priscilla,
Miss Adria.
so you won't ask questions.
Miss Adria, please, I'm fine.
Hey, it.
Australia.
So you won't also ask any question.
No, please.
Hey, Inshira form leader.
Yes, Mr. Yeah.
Okay, so we are saying that the current leads the voltage. So current, the alternating current leads the voltage. And here, yes, VC. Of course, VC is equal to the source voltage because this is the only actor or actress in the movie. Now, what is the equation of the instantaneous current flowing through the circuit? I is given by Im sine omega t. What is the expression for the instantaneous voltage? Vm sine omega t. This capacitor has capacitance C. So, but we also know that the current flow I is given by change in Q over change in T, or Q over C. Q over T is current. Apart from this, capacitance is also given by Q on V. Please look at how I'm writing the equations. This has to do with the fact that we are talking of alternating source. So all these are there. This I is an expression for current. Electric current is charge over time. Capacitance of a capacitor is the ratio of the charge, magnitude of the charge over the potential difference. Please, are you okay up to this stage?
Yes, sir.
All right. Let's make Q the subject in equation 2. If you make Q the subject in equation 2, we have Q is equal to CV. Let's substitute this into equation 1. If we substitute Q is equal to CV into equation 1, this is what we have. We have I is equal to CV over T. So it means the current flow is equal to C times the change in voltage divided by the change in the time. Please, are we okay up to this stage?
Yes, sir.
And should I respond? Are you?
This this I don't understand what you just like. Where the DVDT come from?
All that I'm saying is we have I, a current being equal to capacitance times the voltage over time. But because the voltage within a circuit is a sinusoidal, instantaneous change, it changes with time. The reason for which I brought dV over dt, meaning the voltage within changes with time. So if you see dd, then we are looking at the change. Are you okay?
Yes, please.
All right. Now, what is the voltage? The instantaneous voltage within is this. So we have I is equal to C del over T. What is V? V is this, the instantaneous voltage. So V M sine omega T. Meaning we are differentiating what we have within the brackets with respect to time. This is a coefficient. It's not affected. So C times Vm will come out. Then we have del dt of sine omega t. Because of SHM, at least we understand this. Okay, so you differentiate the delta function. You differentiate the delta function omega c Vm, then you differentiate the mother function. When you differentiate sine omega t, you have cos omega t. Please, are you okay up to this stage? Are you okay up to this stage?
I don't understand the last statement.
We are, you see, we are differentiating whatever we have within the bracket with respect to time. But in differentiation, the coefficient is not affected. So this is pulled out to multiply this. So we have C times Vm del dt of sine omega t. So we are actually differentiating what we have within the bracket with respect to time. But this is a function of a function. We have omega t within sine. So you need to differentiate this small function with respect to time. When you finish, you differentiate the mother function sine omega t with respect to time. That's what I mean. So the differential of the daughter function, okay? So, okay, so we have del dt of omega t times del dt of sine omega t. When you differentiate omega t, it's equal to omega. So omega, then when you differentiate sine omega t, it's equal to cos omega t. So the differential of this, the differential of what we have here is equal to, this is constant, this is constant. So we actually have omega cos omega t as the differential of what we have here. Insha, are you okay?
Yes, please.
All right. So when we compare these two, y is equal to a cos omega t, you realize that this part is equal to what I've clouded is equal to what? This is equal to
A.
good. So this is the maximum current. Please, this is current I. Instantaneous current is equal to this. So what I've put within the bracket is the maximum or the peak current. Please, are we okay?
Yes, sir.
Edith, Gerard, Irene, Shira, and Priscilla, are you okay?
Yes, please.
What I've put within the bracket is the maximum current, similar to the amplitude, the maximum displacement. So I can say that I maximum is equal to omega C V maximum. It's more or less like equating this to this. But since it's current, what is here would also be maximum current or peak current. So I maximum is actually equal to whatever I put within the bracket. Now let's divide through by Vm. Divide through by Vm. So we have omega C is equal to Im over Vm. But current and voltage, we always express it in RMS value. So please express maximum current and maximum voltage in RMS value for me. Start work. So do it and then give me whatever you had for I maximum, whatever you had for V maximum in terms of RMS value. I hope you understand.
No, please. What did you say?
Let's express the maximum current and maximum voltages in RMS values, not in maximum or peak values. I want them expressed in RMS values.
Yeah.
Yes.
Please, I had WC is equals to I over IRMS over VRMS.
So this will be I RMS times root 2. Then the denominator would also be VRMS times root 2. And at the end of it, the root 2's will cancel off. Now, if you have I divided by V, what will this amount to? I over V.
Inverse of resistance.
All right. So it is, you see, this actually from Ohm's law, you have a friend of resistance. But because the component we have here is not a resistor, we can't say that this is resistance. But this is also resistance offered to the flow of current by a capacitor. And so it has its own name. Okay, because the component we have here is a capacitor. And we seem to have had the resistance offered, okay, to the current by the capacitor. We call this I over V as 1 over capacitive reactance. So the capacitive reactance, which we are representing as XC, is the opposition to the flow of alternating current by a capacitor. If the device is a resistor, then we will call the opposition as resistance. But over here, because the opposition, the device is a capacitor, the opposition offered to the flow of current, we will call it as capacitive reactance. So I over V is the inverse of the capacitive reactance. So where 1 over Ix subscript C is equal to omega C, then you define where Xc is known as the capacitive reactance. So it's like we distinguishing between the opposition. If it's a resistor, its opposition is resistance. But when the device is a capacitor, we are not calling it as resistance, but capacitive reactance. Please, are you okay? Isra, are you okay? Edith and Co.
Yes, please.
So we have identified that for a purely capacitive circuit, let's make Xc the subject from what we have. Let's make Xc the subject. If 1 over Xc is equal to omega C, let's make Xc the subject. Xc is equal to 1 over omega. So we are saying that capacitive reactance is equal to the inverse of. So Xc is equal to 1 on omega C, which is also equal to 1 over omega is 2 pi F. 2 pi F C. The SI unit of capacitive reactance is the same as the SI unit of resistance, ohm. So this is how.
So please, can you bring the camera down so I can see the bottom? Thank you, sir.
So the capacitive reactance. Okay, let's start from resistance. Resistance is the opposition to the flow of current by a resistor. Then the capacitive reactance is the opposition to the flow of current by a capacitor. By a capacitor. And it is equal to 1 over omega c, where omega is the angular velocity, and then c is the capacitance of the capacitor. So please be defining your terms. Omega is the angular velocity or angular speed, and c is the capacitance of the capacitor. Okay, so let's look at the phasor diagram and then the waveform for a purely capacitive circuit. Gerard, are you through with the right hand?
Yes, sir.
The waveform, the phasor diagram, we are saying that in a purely capacitive circuit, the current leads the voltage. In a purely capacitive circuit, the current leads the voltage. So we got this relation we had for the current through the capacitor. I is equal to omega c Vm cos omega t. Then the voltage drop across the capacitor is equal to the voltage of the source. So this is Vm sine omega t. If you draw this, both of them on a graph, the voltage is a sine function. Start from the origin. The current is a cosine function, which is always start from the peak value, which is the peak value is Im. So what it means is that for purely capacitive circuit, whenever voltage start from 0, current start from the maximum, and the current is always leading the voltage by an angle of 90. This is 0, this is 90. Okay, when this is at 180, current will be at 270. On and on and on. So for a purely capacitive circuit, current leads the voltage by an angle of 90 degrees. For a purely capacitive circuit, current leads the voltage by 90 degrees or pi on 2 radian by 90 degrees or pi on 2 radian. So this is the waveform. Because this is a cosine function always starts from the peak. A sine function always starts from the 0. So when this is starting at 0, this is already at the maximum. In terms of angle, when this is 0, this is at 90. Okay. When the other one comes to 90, the other one goes to 180, on and on. So the current always leads the voltage by 90 degrees for purely capacitive circuit. Please, is it understood? So this is the waveform. This is the waveform. Let me draw the waveform. Now the phasor diagram. The phasor diagram is a vector representation of the relationship between current and voltage for a purely capacitive circuit. The current phasor is always horizontal. Recall that when we drew that for purely resistive, current was put in this direction, and because voltage was in the same line as the current, we added it. So the current phasor always comes first. Okay. So for purely resistive circuit, what we are saying is that the current leads the voltage by 90. So if the current is coming first, then the voltage must be behind it, behind the current by an angle of 90 degrees. This is the phasor diagram for purely capacitive circuit. And this is the phasor, the waveform for a purely capacitive circuit. So the two things involved here are what I've drawn for you. Please, if you have any question, ask.
Mr. Joe,
Hello.
please, I'm not really understanding the graph you have drawn.
Pardon?
I'm not really understanding the graph you have drawn.
How did I draw the graph? You see, we looked at what we had for the current. We saw I to be equal to C V over T. So change in the voltage divided by the rate of change of current. Then we substituted the instantaneous voltage. So C V M, the change. So del dt of the instantaneous voltage Vm on sine omega t. Then we went through the differentiation and then got omega c Vm cos omega t. And this is the instantaneous current flowing through the capacitor, which leads the voltage. And so we plotted the current, a graph of the current and the voltage against time. The voltage, so this is the current. This is actually the peak current, I maximum. Okay. The voltage is the instantaneous voltage Vm sine omega t. So when you plot these two on the same graph against time, because this is a cosine function always start from the magnitude or the maximum value. This is a sine function, always start from 0. So the graphical representation of I and then V is this. Current, when voltage is starting from 0, current is already at maximum, meaning that the current always leads the voltage. Okay, when the voltage, so this is actually VC, whereas this graph is I, the current flow. So the current always leads the voltage. How is that seen? When voltage is 0, vertically, current is maximum. Horizontally, when voltage is at an angle of 0, current is at 90. Isn't it an indication that the current leads the voltage?
Yes, please.
So that is what we mean by the waveform, which explains the graphical representation of the relationship between I and VC. In terms of phasor diagram, vectors, current leads the voltage by 90, and the vector representation is what we are saying to be the phasor diagram. Ishra, are you okay?
Yes, please, I'm fine.
Okay. Edith, Irene, K and Co, are you okay?
Yes,
Edith,
please.
is another
Still
one
here.
so inactive? Okay. Priscilla, are you there?
Yes, please.
Are you fine?
Yes, please.
All right. All right. It's already 4 o'clock. And unfortunately, it's cloudy. I wish we have time to, but I don't know your schedule of other. So let's see if we can continue tomorrow on purely inductive circuits. Is that okay? So please spend time to go over this. Go over all that we've done up till now. How we got XC to be equal to 1 over C, then the phasor diagram, and then the waveform for purely resistive component, then purely capacitive component, and then what we are left is a purely inductive component, which we will look at it tomorrow. Okay, so please let's end it here, okay, and continue tomorrow.
Please let me sing the down part, I beg.
Pardon?
Please, I want to see the other side.
All right. Yeah, Gerard, is it raining at your end?
Yes, sir. What
Uh,
to do?
it has started
It has
here.
started raining.
Yeah, it's
Please
heavy
say
here. Hello.
please, I'm done. Thank you.
Okay. All right. So see you.
Bye.
Bye.